All right, so you wanted to deep dive into Hilbert's problems.
Yeah.
And let me tell you, this is going to be a fascinating one.
It is.
We're talking about 23 problems presented by mathematician David Hilbert
Right.
back in 1900.
Wow.
These weren't just homework assignments, you know. They were meant to guide, like, future math research.
Yeah, it's amazing to think about it, a list of problems shaping like an entire century of mathematical discovery.
Really is.
Some of these problems were solved like relatively quickly.
Right.
Others took decades of just intense work.
Yeah.
And some, oh well, some are still stumping mathematicians to this day.
It's incredible. So imagine yourself back in 1900.
Okay.
The dawn of a new century.
New century.
There's this like electric feeling in the air. Science is on the verge of breakthroughs.
Absolutely.
And in the world of mathematics, there's this palpable buzz of excitement.
Hilbert stepped onto the stage at the International Congress of Mathematicians and presented these 23 problems, carefully chosen. His idea was that the solutions to these problems would unlock entirely new areas of mathematics, revealing hidden connections and pushing the boundaries of what we knew.
And some of them really did just that.
They did.
Take problem number 3, for example.
Okay, number 3.
It sounds pretty straightforward at first.
All right.
Can you take one shape, cut it up into pieces, and perfectly reassemble those pieces into a totally different shape?
You might think, like, sure, why not?
Yeah.
But the answer turned out to be no. You can't always do that.
Whoa.
And one of the most surprising discoveries was that you can't transform a regular tetrahedron, a pyramid with 4 triangular faces, into a cube using this cut and reassemble method.
So that's what I love about this.
Yeah.
The answer's unexpected.
It is.
It really makes you think. It's like these problems are full of hidden surprises.
Absolutely.
And speaking of surprises,
Okay.
let's talk about the one that really captured Hilbert's imagination.
Problem number 8.
Problem 8.
The infamous Riemann hypothesis.
Ah, the Riemann hypothesis.
This one has been a real head-scratcher for mathematicians for over a century.
Over a century. It delves into the world of prime numbers. Those numbers that are only divisible by 1 and themselves.
Right.
Essentially, it's all about trying to find a hidden pattern in the way prime numbers are distributed.
And the fact that it's still unsolved after all this time just adds to the mystery, right?
It does.
I mean, Hilbert himself said that if he were to wake up 1,000 years in the future,
oh, wow,
the first thing he'd ask is if the Riemann hypothesis had been solved.
Really?
That's how much this problem captivated him.
Hilbert really believed in the power of math to unlock the secrets of the universe.
Yeah.
And, you know, that unwavering belief is evident in so many of his problems.
Okay.
Like problem number 6, for example.
Okay, what's number 6?
This one asks whether we can describe all of physics using math.
Whoa. So we're not just talking about equations for gravity or electricity here.
But, like, literally everything in the universe.
Everything. It really gets at this question of whether math is just a tool we use to describe the world, or if it's somehow woven into the very fabric of reality.
Now, as we dive deeper into these problems, you'll see just how varied they are.
They are.
Some dealt with pure numbers, others focused on geometry.
Yeah.
And some, like problem number 6, really blurred the lines between mathematics and other fields like physics.
And what's fascinating is that Hilbert believed every single one of these problems could be solved.
Really?
He had this unshakable faith in human ingenuity.
Wow.
But, ironically, his own list would eventually challenge that belief in a very profound way.
Okay, now you've got me really intrigued.
Yeah.
What happened? What could shake Hilbert's faith in the solvability of all mathematical problems?
Let's just say Hilbert's problems led to some truly groundbreaking.
Okay.
And perhaps even unsettling discoveries about the very nature of mathematics itself.
All right, well, I am definitely hooked. But before we jump into the next batch of Hilbert's mind-benders, I want to hear from you, the listener.
Yes.
What's standing out to you so far?
Yeah.
Which problem has you the most intrigued?
Right.
Let us know because, trust me, we've only just begun our exploration of these fascinating mathematical challenges.
We have. It's remarkable how Hilbert's problems acted as, like, springboards for entirely new areas of mathematics, even those that remained unsolved.
Oh, wow.
Like, take problem #10, for instance.
Ooh, what was that one about?
It asked if there's a way, a step-by-step process, to figure out if any equation you can dream up has a solution with whole numbers.
So, like a universal equation solver.
Exactly.
That's like something out of a sci-fi movie.
But here's the twist.
Okay.
The answer which came decades later, turned out to be NO.
Oh, wow.
There's no such magical algorithm.
So even improving something was impossible.
Yeah.
Hilbert's problem led to a breakthrough.
Absolutely. It had huge implications for what we understand computers can and cannot do.
Yeah.
It's a great example of how these problems weren't just about finding answers, but about pushing the boundaries of mathematical thought itself.
It's really making me rethink how I view math.
Right.
It's not just about formulas and calculations. It's about these deep questions about what's possible, what's knowable.
Precisely. And some of those questions were answered in pretty surprising ways.
Oh, okay.
Remember we talked about problem #7?
Uh-huh.
And those transcendental numbers?
Now, transcendental numbers, that sounds intimidating.
It can be.
But I think I get the gist. It's like they exist on a different plane than our everyday numbers.
You're on the right track.
Okay.
Think of it like this. Most numbers we deal with, like whole numbers, fractions, even decimals, can be expressed as roots of equations.
Okay.
We call those algebraic numbers.
Right.
But transcendental numbers, like pi or e, they can't be pinned down that way.
Oh.
They're rebels, forever going on infinitely without repeating.
They're kind of like the wild cards of the number world.
I like that analogy.
Thanks.
Now, problem #7 asks, what happens when you take an algebraic number and raise it to an irrational power?
Okay.
Will you always get a transcendental number?
That's getting a bit complex for my non-mathematician brain.
It is.
What's the verdict?
The answer is a resounding yes.
Oh, wow.
Thanks to the work of brilliant mathematicians like Alexander Gelfand,
okay,
we now have a theorem that confirms this, a cornerstone of number theory.
So Hilbert's problem sparked a whole new theorem.
It did.
That's pretty awesome.
It is.
And I'm guessing this wasn't the only problem that led to these kinds of breakthroughs.
Not at all.
Really?
Remember problem #3? The one about cutting shapes and reassembling them?
Yeah.
Well, that led to the development of din invariants.
Okay, you lost me again.
Okay.
Then what now?
Think of them as special tools that help mathematicians analyze geometric figures. It's like having a set of measuring instruments to figure out the properties of a shape. But instead of measuring length or width, they're measuring something more abstract.
So it's like Hilbert's problems were these seeds that grew into these massive trees of mathematical knowledge.
Good analogy.
I'm sensing a but coming, though.
You're right to sense that not all of Hilbert's problems were home runs.
Oh.
Some, like problem #4, turn out to be, too vague.
What was problem #4 all about?
It asked mathematicians to find all the possible geometries where the shortest distance between 2 points is a straight line.
Yeah, I mean, a straight line is the shortest distance, isn't it?
That's what we usually think.
Right.
But as mathematicians dug deeper, the very definition of geometry started to expand.
Okay.
It turned out Hilbert's original wording didn't quite capture the complexity of the concept.
So it's like he was asking them to map a territory that was constantly shifting and changing.
Exactly. And then there's problem #6, the one about describing all of physics with math.
Right.
It ran into trouble because, well, physics itself went through a revolution in the 20th century.
Oh, right.
Quantum mechanics came along and, shook things up.
Ah, so it's not that these problems were bad or unimportant, but rather that the landscape of mathematics and physics shifted in ways Hilbert couldn't have predicted.
Precisely, and that, I think, is a valuable lesson in itself.
Yeah.
It reminds us that even the brightest minds are working within the context of their time.
Right.
Knowledge is always evolving.
Yeah.
And sometimes the questions we ask have to evolve along with it.
I'm really starting to see the brilliance of Hilbert's vision here.
Yeah.
It wasn't just about getting the right answers. It was about asking the right questions.
Right.
Questions that would push the boundaries of human understanding, even if they didn't have neat and tidy solutions.
Absolutely.
It's about the journey of exploration.
It is.
The challenge of pushing the limits of what we know.
Right.
But we've only scratched the surface here.
We have.
And there's one more piece of this puzzle that I'm really curious about.
Okay.
We talked earlier about Hilbert's unwavering faith in the solvability of all mathematical problems.
We did.
But you hinted that his own list challenged that belief.
Ah, yes. That brings us to perhaps one of the most mind-blowing discoveries sparked by Hilbert's list.
Okay.
It's a concept that shook the foundations of mathematics.
Wow.
And continues to fascinate and challenge us to this day.
Okay, so we've talked about the solved problems,
Right.
the unsolved ones,
Yeah.
and the ones that turned out to be a bit too vague.
Yeah.
But you mentioned something that really shook things up.
Yeah.
Something that challenged Hilbert's belief in the solvability of all math problems.
It did.
What was that about?
That brings us to Gödel's incompleteness theorems.
Okay.
They're a bit tricky to explain, like in simple terms.
Right.
But essentially, they demonstrate that there will always be true statements in mathematics that we can't actually prove.
Whoa, hold on.
Yeah.
True statements that we can't prove.
Right.
That sounds almost paradoxical.
It is a bit mind-bending.
How can something be true if we can't prove it?
It goes against our intuition about how math should work.
Yeah.
But what Gödel showed was that any system of logic complex enough to encompass basic arithmetic will inevitably contain statements that are true but unprovable within that system.
So it's like there are these fundamental limits to what we can know for certain.
Limits to what we can prove.
Even in mathematics, a field that we often see as the epitome of logic and certainty.
Exactly, and that's why Gödel's theorems were so revolutionary.
Yeah.
They essentially shattered Hilbert's dream of finding a single all-encompassing system that could prove or disprove any mathematical statement.
You know, it's almost like mathematicians stumbled upon a hidden door in the mansion of mathematics.
I like that.
And what they found behind it, it wasn't just another room, but a whole new wing they never knew existed.
Full of questions about the very nature of truth and proof.
A whole new set of challenges.
Did that discovery fill them with more excitement or more uncertainty?
I think it was a mix of both.
Yeah.
On the one hand, it was unsettling to realize that there were these inherent limits to what mathematics could achieve.
Right.
But on the other hand, it opened up a whole new realm of inquiry.
Okay.
A deeper exploration into the foundations of mathematics itself.
It's like the more we learn, the more we realize how much we don't know.
It's true.
And that can be both humbling and exhilarating.
Absolutely.
But even with these limitations, Hilbert's problems had an undeniable impact, right?
Oh, absolutely. Despite the fact that some remained unsolved.
Right.
Or perhaps even because some remained unsolved. They spurred generations of mathematicians to explore new ideas. Develop new techniques. And push the boundaries of the field.
It's like Hilbert created this roadmap for mathematical exploration.
A set of challenges that would guide mathematicians for decades to come.
I like that analogy.
And even though the map might not have been perfect,
right,
it led to incredible discoveries along the way.
Absolutely. And that, I think, is the true legacy of Hilbert's problems.
Okay.
They weren't just about finding answers.
Right.
They were about asking the right questions.
Yeah.
The questions that would spark curiosity, inspire creativity, and ultimately deepen our understanding of the universe and our place within it.
So what does all of this mean for our listener?
Yeah.
The non-mathematician who's been on this incredible journey with us.
Yeah.
What's the takeaway from this deep dive into the world of Hilbert's problems?
I'd say it offers a glimpse into the beauty, the complexity, and yes, even the mystery of mathematics.
Yeah.
It shows that math isn't just about memorizing formulas or crunching numbers.
Right.
It's a living, breathing field full of unsolved puzzles, surprising discoveries, and profound questions that touch on the very nature of reality.
And it reminds us that even in a field as seemingly rigorous as mathematics, there's always room for wonder.
Absolutely.
For exploration.
Yes.
And for the joy of discovery.
Beautifully put.
So to wrap things up, we've explored the fascinating world of Hilbert's problems. A set of challenges that shaped the landscape of 20th century mathematics.
Right.
We've seen how they led to breakthroughs, sparked new areas of research, and even challenged our fundamental understanding of what mathematics can and cannot achieve.
It's true.
And while some of these problems remain unsolved, they continue to inspire mathematicians to this day.
If you find yourself intrigued by any of the problems we've discussed, I encourage you to, delve deeper. Explore further and see where your own mathematical journey takes you.
And remember, even if you don't find the answer, the journey itself is full of intellectual rewards. Thanks for joining us on this deep dive into Hilbert's problems.
It's been a pleasure.
We'll see you next time for another fascinating exploration into the world of knowledge and ideas.